Hello everyone, welcome to one more session of live discussion. Today our topic of discussion is nuclear radiation sensors and what are the available nuclear radiation sensors. I invite Mr. Ashwini Kumar Sinha ji and Suresh Dwivedi ji for this discussion. My first question is, which type of radiation sensor would you choose for a compact battery powered radiation monitor and why? Ashwini, you're on mute. I think you have to turn.
Hello. Yeah. So yeah, there are various kinds of nuclear radiation sensors out there in the market, and for the different purpose, people use different like for the nuclear reactors and measuring or monitoring the nuclear radiation around the nuclear reactors. There are particular kind of sensor they use for taking care of the nuclear warheads, or measuring the nuclear radiation during the nuclear bombs or the warheads. They use certain kind of nuclear sensor, nuclear radiation detection sensor. So before going deep into that, let me tell you what are the nuclear radiations and why it's important for us to take care of these nuclear radiations, and why it's important for us to measure these parameters. In nuclear radiations, there are generally three waves, that is alpha, beta, and gamma. These are the three waves in the nuclear radiation. So, so if you want to measure these three alpha, beta, gamma, these three nuclear radiations. So there are a lot of sensors. One of the common sensor that we often find in the market, easily available for all of us for to prototyping and designing, is what we call the Geiger-Müller tube or Geiger-Müller tubes. It's a different processor for that. And then we have the ionization chambers that also detect the alpha, beta, gamma radiations. Alpha, beta, gamma radiations. And there are few sensors like the semiconductor detectors, like that can also detect. So there are various stages and various different kind of sensors use the different technology to detect the alpha, beta, gamma range. Some also sometimes detect, we need to detect the neutrons levels as well in the radiations. So like there are certain detectors that also use that. And there is a very particular sensors for only for detecting the neutron, that are the neutron detectors, just for the detecting the radiating neutrons from the those material like He3 or BF3 or boron line detectors, or capture the neutron producing from those nuclearly radioactive substances. Okay. And if you ask me for what type of radiation sensor would I choose for the compact battery size designing of the nuclear radiation monitor or a radiation sensing device. So one of the commonly found for easily for research purpose and for even the user purpose, and most of the people even use in the real life, is the Geiger-Müller tube, or you can also say the Geiger-Müller tube. So let me show you one I have. So I have done various designs on that as well. So I am one who have used this for the long times in many designs of me. So let me show you. This is the one of the nuclear radiation detectors that I have created, and this is based on the Geiger-Müller tube. So here in this design, in my design, you can see here there is a tube. You can see tube. This tube is called Geiger-Müller tube, that is used for the detecting the nuclears. Okay, so for if you want to make the battery operated and very compact nuclear sensors or nuclear detectors or want to find the nuclear radiation around your area, then it is the best abundant and easily available things that you can use and design your own. And I have used in many design. I'm using this process for very long time for various experiments of me.
Okay, so how do you choose a sensor for measuring alpha particles in outdoor environments?
Yeah. Choosing a sensor for measuring alpha particles an outdoor environment involves several critical considerations to ensure accurate, reliable, and the durable performance, such as type of the sensor. Alpha particles are highly ionizing but have very low penetration power. They can be stopped by a few centimeters of air or even a sheet of the paper. Therefore, the sensor must have a windowless design or use a very thin entrance window, such as mica, to allow alpha particles to reach the detector. Commonly used sensor type include scintillation detector, solid state detector, for example, silicon surface barrier detector, and gas ionization chamber. Solid state detector are particularly suitable for their compact size and the sensitivity. And the environmental suitability is also very important. Outdoor conditions introduce challenges such as the temperature fluctuations and humidity, dust, and the precipitation. The sensor should be weatherproof and housed in a sealed enclosure with the decent air for swimming systems. So, it is very important to prevent the parameters. So, temperature compensation features can enhance measurement stability. Another parameter is the sensitivity and the background discrimination. Since alpha particles do not travel far in air, the sensor must be placed close to the source. The detector should also be capable of the distinguishing alpha particles from beta and gamma radiation, which requires pulse shape discrimination or the energy resolution capabilities. Power and the data requirements. For outdoor use, consider a sensor that supports battery or the solar power and offers wireless data transmission for remote monitoring. Low power consumption is the critical for the long-term deployment. So the calibration and the maintenance, it is also very important. Select a sensor that supports field calibration and is easy to clean and maintain, especially if deployed in dusty or the vegetated environment. In brief, we may say that the ideal sensor for outdoor alpha particles detection should be combined high sensitivity environment, robustness, energy discrimination, and ease of the deployment of the maintenance. That's all.
Okay, so how do GM tube based nuclear sensor work, and how accurate are they for detecting the nuclear warheads and radiations?
Yeah, so the GM tube, or you can say the Geiger-Müller tube, actually works by using the principle of ionization of the gas. Okay, okay. So so actually, the main part of that whole design is the Geiger tube. That is why we call Geiger-Müller tube. and when it's exposed to the nuclear radiation, the it creates some pulses that can be converted into the reading of the nuclear intensity. So let me explain briefly. So here I have one of the sensor that is used for detecting the nuclear measurement, the nuclear radiation. Either it's the nuclear warheads, or either it's the nuclear radiation from the rocks, marbles, and all other things, or the nuclear radiation from the nuclear reactors like this. You can see these are the nuclear reactors. In the what used in the nuclear reactors for the power plant, nuclear power plant, or nuclear based submarines, and all those things. Okay. So as you can see here in this whole design, there is a tube you can see here. If I open this cover of that, so here is it. You can see there is a tube, and also you can see a mark here. That is the danger mark. So I will explain why there is a danger mark. And so this is the Geiger-Müller tube. So I can remove it like this. So it can be removed. So this is the main part of the whole sensor. This Geiger-Müller tube is the main part of the whole sensor for detecting the nuclear. So this nuclear tube is the main part that actually detects the nuclear. So you can see, if you see closely inside this tube is filled with the gases. Uh, uh, these gases are generally argon or neon, and then all the other gases are vacuumed out, and these two gases are filled. And you can see there are two poles are there or what you can see the uh, two electrodes are there here inside it. Okay, you can see the two electrodes are there. So what happens when the radiation like alpha, beta, or gamma waves that is exposed during the nuclear radiation, either from the rock or nuclear radiation from the warheads, nuclear warheads, or nuclear radiation due to the leakage of nuclear radiation from these kind of nuclear reactors. So when this happens, when the alpha, beta, gamma radiations happens, then it fall on this tube, and when they fall on this tube, they ionize the gas. Okay, and that ionized gas create electrical pulse. Okay, and that pulse being then measured by the sensor, and then that pulse is very weak, very small. Then that pulse is amplified with the help of different amplifier inside the circuit. Okay, and using these different amplifier, we can amplify those signal that is caused by that is being generated due to the ionization of gas inside this tube. Okay, and then that is then converted into the readable reading. Okay, that can be converted into nuclear intensity, how much intense the nuclear radiation is, how much very if it's very high intense, or whatever the intensity, it will change accordingly. The pulse will change accordingly. So now let's look at the working structure of this tube. Uh, so to get the gas ionized, it need a voltage around when the nuclear radiation fall on this, whether it and gas need to be ionized, it needs a very high voltage inside the running inside this tube filled with those gas. So that voltage is typically around 400 to 900 volts. Okay, this is 4000 to 900 volts. Okay, so that's why that is the reason why you see here there is a mark called electrical shock mark. So when the circuit is turned on, when the circuit whole working, the voltage around this Geiler, these two electrodes on this Geiler-Müller tube must be around 400 to 900 volts, and it gives you a very high electric shock here. So one question might arises around your mind. So you have said that in earlier question I have told you that in my design and most of the design for the portable and battery operated nuclear sensors design, I choose this Geiler-Müller tube based design. So and now you are saying that is work around it's need a 400 to 900 volts range. So how can a battery operated thing can get this kind of voltage? So this is not very new. This is very old technology. might have also seen in the old CRT televisions. In the old CRT televisions, the CRT tube need the 1000 volts of the to get the gas ionized inside the tube, and so the picture on the tube in the CRT television. And if you see the input voltage, it's either the 10 to 12 volt. If it's a battery operated television, it's 10 to 12 volt. And then it's if it's the if it is AC operated, then it's just 110 or 220 volt. So by taking 110, 20 voltage, convert that voltage into the 1000 volts. The same thing happen here. I just need to connect the 3 volt or 5 volt battery here. Then the circuit in this create a step up, conversion of the voltage, and creates a voltage around that 3 volt get converted into the 400 or 900 volts. Okay. And that is why it is not you have to careful while using these kind of nuclear sensors, because it give you the shocks if you touch here. That's why we need to cover this part with these kind of materials. Okay, so this is how the Geiger tube works, and they are very accurate if you see, and very reliable as well, and easily available and easy to design as well if you want to make a nuclear nuclear reactor monitoring device or nuclear radiation sensors.
Okay, so how do you handle high voltage requirements in GM tube within a compact PCB design?
Actually, handling high voltage requirement in Geo GM Miller tubes within a compact PCB design requires careful planning to ensure safety, reliability, and the efficient performance while maintaining a small footprint. We have to consider high voltage generation in GM tubes typically require 300 to 600 volt DC. A common solution is to use a DC to DC boost converter, or sometimes use flyback converter to set up a lower voltage input, for example 5 volt or 12 volt, to required high voltage. These circuits can be implemented using compact transformer-based or sometimes charge pump design with the attention to component selection for the high voltage operation. Another parameter is the PCB layout consideration. High voltage testers must be designed with the adequate clearance and the creep-traces distance to prevent arcing or dielectric breakdown. Use rounded trace corner, not sharp angles, and the wide trace spacing to minimize the corona discharge. High voltage areas should be physically isolated from the low voltage and the signal path to avoid the noise and the potential damages. Next parameter which we have to keep in the mind is the insulation and the safety. In this, apply conformed coating or use silicone coating around the high voltage section to improve the insulation, especially in the humid or the dusty environments. Clearly label high voltage area on the silk screen to prevent the handling and the errors. Next parameter, which is very important, size optimization. Because it generates a high voltage, so we have to use high voltage SMD components. For example, resistors, capacitors, or diodes to reduce the board space. Some GM tubes interface modules come in integrated miniature package that can be directly embedded or the socketed onto the main PCB. Next parameter is filtering and stability. We have to include the RC filters and the voltage regulation circuits to reduce noise and they maintain voltage stability, which is critical for the consistent GM tube operation and the accurate pulse detection. So, by carrying these things, when we are designing the high voltage section with the proper isolation, efficient power conversion, and the compact component choices, it is possible to integrate the GM tube into a small PCB without the compromising safety and the performance.
Okay. Okay. So, what are the sizes of GM tubes needed for sensing, and what is available? How do these sizes affect their sensing capabilities?
Yeah. So the size of this GM tube is very essential part. Size and the thickness of the GM tube, this Geiger-Müller tube, is very important here, and it play a key role in the sensitivity and the use cases of these Geiger-Müller tube. So as you can see, if the tube size is small, of this Geiger-Müller tube, uh, then the gases inside this, the volume of the gases is packed inside this for ionization for process. When the alpha beta gamma rays fall on this tube, then the ionization process will need to be happen. So if the tube is small, the gases volume is small, so it also decreases the overall sensing capability of the tube. So the more smaller, if I more if I use more smaller tube, then it will be more less sensible, because the larger amount of the gases it has, there is a chances of larger a larger amount of uh, uh, gases molecules get ionized, because generally if any kind of radiation, nuclear radiations like alpha beta gamma ions, in some case with CPU modification in the circuit, I can even detect the neutron radiation as well. If some neutrons are radiating out from that radioactive substance or some kind of nuclear reactors, then I can simply sense by with some modification of the, I can also detect that as well. So if there is a larger volume of the gas and the tube is also large, then if the same tube is large and then it can consist the large volume of gas that get easily ionized with those radiation, and also the surface area is also got large if we use a larger tube. So chances of falling those radiation on this tube over the surface area is also getting increased, so it will become more sensible in that part. And the second key role plays is the thickness. Okay, so before going to the thickness, the windows thickness, uh, uh, let me tell you that what are the sizes available there for these and for the various purpose. So for the cylindrical end window tubes with the diameter of 0.3 to 1 inch and length between 1 to 4 inch, or you can say 27 to 27.9 to 100 the Geiger-Müller tube. One of the model is the Mullard JP 1481, that is the 76 long and 26 diameter wide the Geiger-Müller tube. And there is another Geiger-Müller tube with the GMT 02, that is 7.7 diameter and 27.9 long. Okay, so 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 these tubes in these range, these tubes are widely available and easily available there in the market. You can find it, and these are generally used for the education purpose and for the prototyping and all those things. Okay, you can get it easily for the prototyping, and they are very less sensible, and they are used in application like detecting the alpha, beta, and gamma radiation in the educational setting, and the portable survey meters to survey out the nuclear radiation at different uh, uh, landmarks or the areas. Okay, and then there is another called the side window tubes, that dimension is around 0.4 to 1 inch, that is 10 to 25 mm. In that range, the their wall, the wall is of the tube is thin that is and they are generally being used in the gamma exposure for rate measurement, or in the even in the industrial use where the nuclear reactors are there or need to be monitored, the need to be monitoring of the nuclear reactors. Okay. And with the few modification, you can also do the neutrons detection as well. There are neutron radiation as well. So there are neutron sensitive tubes are also there. So the dimensions are around the same range, and they are being modified with the boron coating. Okay. Like I've told, with few modification, I can also detect the neutron radiation as well with the same Geiger-Müller tube for the nuclear radiation detection. I can also detect the neutron radiation as well. Okay, so I just need a boron coating over this tube, on doing the boron coating or the boron trifluoride or helium-3, or if we fill the helium-3 gas inside it, or either we can also use the cadmium foil wrappings. If I wrap out the cadmium foil around this with the 0.5 mm of thickness. So if I do this modification, then it can also be used for the for detecting the neutron sensitive, becoming a neutron sensitive tube, and we can also detect the neutron level as well. Okay. So the size of the Geiger-Müller tube affects a lot, and the ball thickness also affects a lot in the sensitivity level. And the larger the size, the larger the amount of gas, and larger the exposure areas to the radiation will be there. So the larger the sensitivity, the greater the sensitivity. The smaller the size, the smaller the what's it? The sensitivity will be. Okay, the smaller the chances of ionizing the gas and getting exposure to the radiation will be there. Okay, so it's affect in that way.
Okay. So how would you design the sensor housing to protect from dust, moisture, and electromagnetic interference?
Yeah. Designing sensor housing to prevent against dust, moisture, and the electromagnetic interference, normally known as EMI, requires a multi-layered approach that balances environmental sealings, material selection, and the shielding effectiveness. First, consider the dust and moisture protection. To safeguard the sensor from dust and water ingredients, the housing should meet at least IP65 or higher standard. Use gaskets or O-rings at all joints and the seals, and ensure that the enclosure is tightly fitted. For sensitive opening, for example, air inlets or the windows, integrate hydrophobic membrane or descent filled vents to allow pressure equalization without letting in the moisture particles inside the cabinet. Next considerable parameter is the material selection. Choose a corrosion-resistant material such as polycarbonate, ABS, or ionized aluminum, depending on the environment. For outdoor use, UV stabilized plastics are the coated. Metal improves durability against sun and the rain. Next, another parameter is the electromagnetic interference, EMI shielding. To prevent the EMI, we have to consider is affecting sensor signals. Use conductive materials for housing like aluminum or the copper-coated plastics, which ensures the continuous electrical contact across some, or use EMI gaskets. For plastics enclosure, internal metallic coating or Faraday cases made of the fine mesh can provide effective shieldings. Grounding the seal properly is very important to divert unwanted currents safely. Next parameter is the cable and the connector sealing. It is also very important. So use shielded cables with the EMI rated connectors and the cable glands with the IP rated sealing. So ensure all external interference, maintain the enclosures over all protection level. Another parameter is the maintenance assess is also very important. So during design, the housing for the easy access during maintenance without the compromising the seals. So use latches or the screws with the reusable gaskets to maintain the enclosure's integrity after the opening. So a well-designed sensor housing integrates environmental scaling, robust material, and the effective EMI shielding to ensure a reliable operation in the harsh condition without signal degradation or the physical damage.
Okay, so how would you design a circuit to discriminate between different energy levels of detected radiation? Should I repeat the question?
Yeah. Got it. I got my point. Yeah. So let me explain a little bit before that as well, because that need that explanation to explain this thing as well. Okay. So when the gas in the Geiger-Müller tube got ionized, okay, due to the nuclear radiations, different alpha, beta, gamma, or the some neutron radiations out there, then these all these sensors work on the mechanism of ionizing of gas molecules due to the radiations. Okay, so when these radiations happens and the gas get ionized, then it pushes the electrons into pairs and produces a electrical pulse. Okay, so in the form of analog signals. Okay, these pulse amplitude around the 0.1 to the 10 volts depending on the tube design and the voltage design. Okay, and with the duration of 10 to 100 microseconds. Okay, these pulse and very sharp rise in exponential decay when there is a burst of these nuclear radiation on this tube. Okay, so after this happening, all these things happening, okay, then you need a certain kind of signal conditioning and pre-amplification circuit in that. Okay, because if the pulse is very small, like I've told you that sometimes it's the amplitude is around 0.1 to the 10 volt. So 10 volt is a good case of scenario. If the very large Geiger-Müller tube we have created with the very high voltage range, but if you have created in this voltage range, then you need then it generating the pulse around the 0.1 volt or even below that. Okay, so this very weak one. So you need to pre-amplification circuit, or you need to amplify it so that you can read up to at least one in the range of 1 to 5 volt in the range of 1 or to 3 volt. Okay, so you need a preamplifier circuit that amplify all those signals. Generally, like here in this sensor, it is used the LM358, or you can use AD620. There are many amplifiers out there in the market. I see that you can use. You need pre-amplifying the output pulse into the up to the voltage range that you can convert them into the readable range. Okay, then there you need, after that amplification thing, then you need a filtration process, because there might be pulses out there, might be some pulses out there, there might be some noise in the signal that will be created. Then you need a high pass filter or low pass filters. Okay, now let's come to your question. So your question is how I can design the sensor to detect the different energy levels. Okay, So now we have amplified the signal. We have amplified the signal that is coming out from this Geiger tube, Geiger-Müller tube, and getting this output pulse, amplified output pulse in the readable range to 1 to 5 volt. Okay, and then that output is going given here. So now at the output, we can add the microcontrollers to read the voltage range, and we can create a different threshold level. So based on different energy levels, the threshold level can be crossed. Like at very low intensity of radiation, it produces the amplitude range of 1 volt to 1.5 volt or 1.8 volt or 2 volt. Okay, then if when there is more higher radiations, when there is more intense radiation exposure out there in the environment, nuclear radiation out there in the environment, then its intensity, again the pulse intensity rise up to the 2 volt to 3 volt range, and then again more higher, very high radiation nuclear radiation out there in the, and it get exposed to that, then the radiation the ionization process will also become high and creating more intense pulse and more high amplitude pulse in the range of 3. So we can add the microcontrollers to process all these signals, the pulse breath, the pulse timing, and the pulse what is the pulse beat, and what is the amplitude of this pulse, and based on those different methods and reading from those from the microcontroller, we can create different threshold levels for the different levels of radiation, and we can able to detect that this is the radiation level, this is the radiation. So we can and then we can also do the threshold optimization based on the different test samples. Like we can create a ideal test sample that where we know this is the radiation level, and this is the radiation that we know this is that much of radiation level. Then we can create and calibrate our test model, our current working test model, with that ideal test models to and optimize the threshold for identifying the different levels of the radiation, and so using these different methods we can do that.
Okay, so how do you simulate radiation events in lab testing without using actual radioactive sources?
Yeah, can you repeat the question?
Yes, how do you simulate radiation events in lab testing without using actual radioactive sources?
Yeah,
Okay.
I also want to take this question a little bit. Yeah, okay. So after me, let us raise Dwivedi to answer. Okay. So there is a very interesting fact that I want to share you. That why I'm taking this question in the middle of that. Sorry for that, interrupting you. Okay. So uh, uh, it's many of the people might not know about this, that nuclear radiation not only found in the radioactive substances like uraniums and all those radioactive materials out there, or not only found in the nuclear reactors like these that you can see here in the photo, or not only find in the nuclear warheads like uranium or other nuclear based warheads, or the nuclear radiation also present in the rocks as well, the marble that you use in your homes. Okay, so the marbles that there are various marble rocks like granite, graphites, and various marbles that you see out there that you use in your home. Some of the if it is a real stone, if it is a real marble that is being dug out, or that is being that is being uh, that you mine from the natural resources, natural ores. So you have created that marble from the mining the hills or the land, or naturally abounded marbles and the granites and various stones. They also exhibits a very small amount of nuclear radiations. Okay, so like if you use the very large amount of marbles, if you're using the very large amount of marble in your home, and that is a natural marble, not the artificial one, or not one duplicate that look like a marble. It's the actual marble that is abundant, that you have extracted from the nature. then it exhibits some kind of radiation. There's some kind of nuclear radiation, and when I use this sensor, then I can see those nuclear radiation reading on the sensor because of those marvels. So we can use those things. We can even if you don't have the nuclear or radioactive material like the uranium, because those are very dangerous. You can't find those, and it's not legal to you to have those with you. So if you want to test these kind of nuclear sensors and want to do the testing for your education purpose, or in the lab for testing, want to test your sensors, how to test sensors is performing, then can use these marbles, the nuclear, these marbles, white marbles and very granite, graphite, naturally abounded marble that you use in your home, exhibit some nuclear and carry some nuclear property, radioactive property inside that. They also radiate some very small amount of nuclear radiation as well. So this is the one thing that you might not have heard about. And there are various articles out there in the online, you can search it there. There are various homes that use the very large amount of natural marvels, very large amount of, if the home is made of very large, like bathrooms current days, the homes and the luxury bathrooms are not now being used, now they are being designed by using the natural marvels and the graphites they carried they in the homes and even in the hotels. So there are various research paper out there, and there are various uh, studies out there in the online. I am not confirming this that they are real or not, but there are various articles out there on the line that if the peoples are having lots of marbles inside the home, the natural abundant marbles, then they exhibit, they are in the exposure of the nuclear radiation, very small, even though it's a very small amount of radiations, they exhibit some kind of diseases, and they are more prone to the cancers and many different kind of diseases that is caused due to this nuclear radiations. So that is one of the things that I also want to say, that yeah, there are some rumors. I don't know if it's the rumors or it's the proof scientific theory, but there are the articles out there that people are claiming that having the very large scale of marbles, natural mountain marbles and granite in your homes or bathroom designs that exhibits a very small amount of nuclear radiation, and when your body exposed to, like you are living in your home with the marble created with the marbles and granites, and they are radiating very small amount of, even though it's very small amount of nuclear radiation, but it's, you are living in the home for 24 and 7 hours, or for larger amount of time you are sleeping in the home. And if your home is made of complete marvel, then they are continuously radiating very small amount of nuclear energy to you, and you are exposure to that. So there are various articles that claims that they are impacting the health of human as well. But I'm not claiming here from my part that because there is no scientific proof yet that made that these claims are true, but there are the articles. So my point is that if you don't if you want to do it for the educational purpose, you want to do doing designing for the educational purpose and for the learning purpose, and if you and if there is no nuclear radiation to test out your these kind of sensors, then you can use those marbles, naturally abundant marbles and the granite, graphite stones. They also carry a very small amount of nuclear radiation as well, and you can measure them by using these sensors. And now go to the Suresh sir, if you want to add many more things to my point.
Suresh sir, you're on mute. Suresh sir, you are on mute.
Yeah. Just I want to include some simulated radiation events in the lab, how we test without using the actual radioactive sources. For simulating radiation events without actual radioactive sources is a very safe, flexible, and the cost-effective laboratory testing. For example, electronics signal injection. Radiation sensors typically convert radiation into the electrical signal by injecting simulated signal directly into the sensor electronics. You can mimic the response of the actual radiation event. This allows the controlled testing of the sensor's output and the response time. Another is the pulse light sources. For photodiode based are the scintillation detectors. Pulse LEDs are the laser can also simulate the light produced by the radioactive interaction. By adjusting pulse intensity and the frequency, different radiation event profiles can be mimicked. Software emulation is very important. The soft sensor firmware are the associated data acquisition system can be tested using the software. So this is a particularly useful during the development to validate signal processing and the response algorithm without the hardware exposures. X-ray tubes and the shielding for controlled gamma are the X-ray simulation, low power X-ray generators with the collimation and the shield can be approximate radiation exposure without using the isotopes. While not entirely source-free, they are safer and the more magnetic than the traditional radioactive sources. Environmental noise testing. Background environmental signals such as the cosmic rays or electrical noise can sometimes be used for the baseline response characterization, although this method is limited and less precise. So, applying these methods helps validate functionality, calibration routines, and the software processing in a safe lab setting. Without they cannot fully replace radioactive sources testing for final verification. They significantly reaches the need for the live radiation during the development and the routine checks.
Okay. So, how do you ensure low power consumption for radiation monitoring in remote or wearable devices?
Yeah, can you repeat?
Yeah. How do you ensure low power consumption for radiation monitoring in remote or wearable devices?
Yeah. Uh, so ensuring the low power consumption for the radiation and monitoring the remote, if you want to do the remote monitoring, suppose that if I want to use the sensor and deploy the sensor for remote monitoring, I need to add IoT device and all those things. In case of Geiger-Muller tubes, it itself needs a very high voltage at this tube range, around this tube. Okay, and due to that, it creates also there is a loss out there. So the Geiger-Muller tube itself requires the voltage range around the 400 to 900 volt, and or some even detects needs the 500 to 1500 volts. It's a very high voltage. And when you are converting the small amount of DC voltage to that range, there is a lots of loss there. And when you are again adding your own IoT microcontroller or the IoT modules to remote monitoring, then they again create a lots of energy consumption as well. So from your side, you can do various kind of optimization in the circuit. Like one is the voltage optimization circuit. So you can operate the GM2 at the lower end of voltage like 400 volt. Like there are various GM2 like SBM20. Instead of using the 500 volt, you can use the 400 voltage range in the DC-DC conversion. You can also enable the HV, the high voltage supply, only during the measurement period. So like if you're not continuously monitoring the thing, like if I want to monitor the radiations at the day, at the night 2 times, or even at the day at the evening, and then at the night, then I can simply turn on these Geiger-Muller tube, the voltage around this Geiger-Muller tube around that reading time when I want to read, not the continuously. So if I continuously keep this thing on, and then that a small 3.3 volt or 5 volt DC voltage being need to be converted to the using the buck booster to the 400 volts or 1000 volts for the some kind of Geiger-Müller tube. Then if it is in continuous loop in the and continuously producing and running this Geiger-Müller tube at the 400 volts, then there are lots of energy degrade energy dissipation will happen and energy losses will be happen. So instead of keeping this tube always on, you can keep this tube on for the period of time when you need to actually actually measure the things. That is one of the optimization mode you can do there. Then again is you can adding the sleep modes, like you can add the sleep mode. So when you now need to measure, then you can put the whole thing device in, so you can shut out the voltage, not only voltage of this Geiger-Müller tube that 400 500 volt, but you also need to shut down the whole amplification circuits, and then also need to shut out the the wireless transmission modules like the Wi-Fi, VLDO, LoRaWAN, whatever you are using along with this tube. Okay, so these are various optimization process that you can use. Okay. Yeah.
Okay, so what failure modes are common in radiation sensors, and how would you design to mitigate them?
Radiation sensors can experience several common failure modes, particularly in demanding or long-term use environments. Key failure modes include radiation damage. So first, prolonged exposure can degrade sensor material, for example, scintillator semiconductors, leading to reduced sensitivity or drift. Mitigation: choose radiation hardened material and the design for the periodic recalibration or the replacement. So use shielding to reduce the cumulative exposure where possible. Next is the electronic drift or the noise. Aging components and the environmental factors, temperature, humidity, can cause signal drift or the increased noise. Mitigation, so include temperature compensation circuits, high quality shielding, and the auto zeroing algorithm in the design. Next parameter is the power supply instability. Fluctuating or the noisy power can introduce the measurement errors. What is the mitigation? So use a regulated power supply, filtering capacitors, and the watching timers to ensure the reliable power supply or the operation. And another parameter is the connector or the solder joint failure. Vibration, thermal cycling, or corrosion can cause mechanical failure. What is the mitigation? Use ruggedized connectors, conform coating, and the mechanical strain reliefs in the assembly. Next is the data communication failure. Errors in the digital interference, for example, I2C, UART, may cause loss of the reading or incorrect data. What is the mitigation? Implant error checking, for example, CRC, redundancy in critical data paths, and watchdog recovery features. Next is the false positive negatives triggered by EMI backgrounds noise or crosstalk between the channels. So what is the mitigation? Include filtering algorithm, signal averaging, and the physical separation of the high voltage and the signal lines. So designing for the reliable and the involves not just robust hardware, but also diagnostic failure, such as the self-test, status plan, and the fail-safe mode. These allow system to detect and respond to fault before they affect safely or the data integrity. That's
Okay, Sureshi. I think this was my last question for the session. So if you have any question, you can post in the comment section. We will come back to you in the next session. Thank you for your time.